My name is David Sliney, and I'm a biophysicist that has been very much involved over the years with optical radiation hazards. And today we're going to examine ultraviolet disinfection, generally referred to as GUV or germicidal ultraviolet. I have no financial conflicts to report, and we'll start by introducing this subject and pointing out that germicidal ultraviolet is really not a new idea. And it was developed back in the 1920s and 30s when low pressure mercury discharge lamps were developed and found to be highly effective in disinfecting microbes. And it was widely used back in the 1950s when there were no vaccines for measles, mumps, polio, and so on. Since there's no current vaccine for tuberculosis, it's still widely used where tuberculosis is endemic in other countries. And it's still widely used in TB hospitals and TB wards in the US. There was quite a renewed interest with the SARS-CoV-2 pandemic. There was a little bit of burst of interest when TB was showing up in prisons and homeless shelters about 25 years ago. And now there's quite a bit of interest in improving the technology. We have new types of lamps, and it can be the one really effective means to disinfect air in occupied settings. But there are potential safety issues, and these are not widely understood. And as a result, we have a lot of unwarranted concerns. Now, any mention of ultraviolet, we need to point out the electromagnetic spectrum. And ultraviolet is that part of the spectrum that is of shorter wavelengths, higher photon energies than visible light. There's a little overlap of visible light into the ultraviolet, but the ultraviolet is broken down, as shown here, into different bands depending upon your specialty. But in photobiology and medicine, we use the International Commission on Illumination's bands known as UVA, UVB, and UVC. You may have heard of UVA and UVB in connection with safety with sunlight and various types of lamps and sunscreens that protect against UVA as well as UVB. And these terms are not totally unknown by the general public. Most people have little knowledge about the shortest wavelengths, which are blocked by the atmosphere, and these are known as UVC at wavelengths below 280 nanometers. Now, since these spectral bands were developed for photobiology and photomedicine, they have meaning in terms of different biological effects, and we shall review some of that. But the real key as to why UV is generally considered more dangerous, if you will, than visible light is the photon energy. Remember, as you go to shorter and shorter wavelengths and also higher frequencies, individual photon energy increases, and therefore it can produce photochemical reactions. So the CIE spectral bands have quite a history. They go back to the 1930s, and it's quite fascinating that they work well in considering photosynthesis and the biological effects of light and UV on plant life, as well as the skin and eye tissues and internal tissues. And the reason is that they're based upon penetration depth into water and into different biological tissues, and also upon the absorption of proteins and certain key biological molecules. So we have actually 3 bands in the infrared as well, but that's not the subject of today's talk. The photon energy is terribly small amount of energy that we would normally consider. So we're being exposed to 10 to the 18th or 10 to the 20th photons per second from sunlight. If we go down to 254 nanometers, we can actually calculate the energy. It's incredibly small, but it's of importance when this photon energy is absorbed by key molecules, because it can alter the molecule, it can break bonds, it can isomerize. And the key rule of photochemists is that one photon interacts with one absorbing molecules. So obviously, you need millions of photons to alter a microorganism, even a virus. In recent years, we've started to break down the ultraviolet C band into further details because of newer discoveries of different types of effects in different parts of the ultraviolet. UV falls in the spectrum between X radiation and visible light. It's termed UVC. The wavelength extent of the full UVC band is from 100 nanometers to 280 nanometers. The little Greek lowercase l or lambda there is what physicists always use to symbolize wavelength. And we'll use that in this lecture. So there's been a new interest, but no really formal definition in what's termed the far UVC. And you see that right between about 200 and 230 nanometers on the scale. So there's a suggestion by some scientists that work in this area to standardize on 200 to 230 nanometers, which in terms of the full UV spectrum is practically in the middle. What about shorter wavelengths that are listed on our image there as vacuum ultraviolet? Vacuum ultraviolet has that term because UV photons really will hardly penetrate a few centimeters of air, and you'd have to work within a vacuum chamber to employ any vacuum UVC. So technically, UVC goes down to 100 nanometers, but many places you'll see it referred to as stopping at 200 nanometers, or at the shortest, maybe 180 nanometers. All right, so what do we mean by germicidal radiant energy? UVC is almost exclusively used for air, water, and surface disinfection because these are the highest of UV photons available. Now, it's important to distinguish between the benefits and risks of the different spectral bands. The longer wavelength photons in ultraviolet B, between about 295 and 315 nanometers that are in sunlight, are less effective for germicidal effects, but are the primary actinic rays that are present in summer sunlight. And most of our occupational safety concerns really should focus on the UVB in sunlight, but we'll get to that later. It should be noted that UVA and even shorter visible wavelength of violet light have been reported to have photobiological effects on some microorganisms, but it's a different form of action, and it requires thousands of times or even millions of times more energy to disinfect at those wavelengths than UVC. So you'll see some advertisements for lamps that supposedly have some disinfection power that are, quote, safer, unquote, than UVC, but they're really impractical. There's a lot of specialized terms that are used when we're talking about optical radiation, such as visible, infrared, and ultraviolet, in laser safety, in these different fields. And I'll just go over these briefly. The radiometric terms are normally standardized by the International Scientific Organization and Illuminating Engineering Society and the International Commission on Illumination, the CIE. And they're used in photomedicine, phototoxicology, safety, and in applications of optical radiation and light. Because of the term radiation to the general public is often a scare word because it's associated for most people with nuclear things and ionizing radiation. A lot of the people in the lighting industry try to avoid using the word radiation. And I think that is justified, even though as a physicist, I'd like to be more precise and consider it's all radiation. We'll often refer to as germicidal light, which is to a physicist not really correct because light is supposed to be visible, but it's more communicative to the public and workers. When we're describing a lamp's output, we often talk about the radiant power. Now, that's normally thought of as the electrical input power in watts, because that's when you buy a lamp, it specifies electrical wattage. But to optical scientists, the important thing is how much energy comes out. That's called the radiant power as opposed to the electrical power. That is actually measured by test labs, but doesn't have a whole lot to do with safety. Radiant energy in joules is how much has been put out in a certain time. Irradiance is an important dosimetric quantity because it's a surface dose rate, that is the watts per square meter or per square centimeter. For talking about sunlight, we normally would talk about irradiance in watts per square meter. But in medical applications, and certainly in terms of exposure to the eye, watts per square centimeter make more sense. And that's widely used in the biomedical community. Radiant exposure then is the irradiance multiplied by the time in seconds, and that's expressed as joules per square centimeter and often referred to as dose. And there are other quantities for specifying light levels, normally lux, which are lumens per square meter, and that's only useful for describing visible light. Now, I've mentioned that in photobiology, it's important to think of individual photons interacting with individual molecules. And there are a few basic concepts that are very important. The first is the Bunsen-Roscoe law of photochemistry. And another way of describing that rule is what's termed reciprocity of dose rate, capital E, and duration of exposure, time t. So irradiance times t is equal to the radiant exposure, and that normally will produce the same biological effects. In other words, if I have a flash lamp and deliver 1 millijoule per square centimeter on my skin, the biological effect is going to be the same thing as with a much lower power lamp, which gives the same millijoules per square centimeter, but its dose rate is much, much lower because it might take 10 or 15 minutes to achieve the same exposure dose. So that's what we mean by reciprocity. You can have a high irradiance for a short duration, or we can have a low irradiance for a long duration, and the biological effect should be the same within certain regions, from maybe microseconds out to a couple of hours. After a few hours, there's some biological repair and so forth, and this starts to break down when we're talking about potential safety hazards. So the power divided by the exposed surface area is irradiance, and in air or in penetration of tissue, there is another term that is used by photobiologists, and that is fluence. It's still in power per unit area, but as we'll see, has a little bit different meaning. And that's important technically, and that is all the safety limits and permissible exposure guidelines are specified in irradiance and radiant exposure, as we see on those top two panels. It's the power per unit area or energy per unit area. Now, the bottom two panels look like the same. They have the same units of power per unit area and energy per unit area, but it includes backscatter and so forth. The concept is that you have a tiny little area deep into tissue, and it's being exposed to the rays that are penetrating, but also quite a bit of backscatter. Now, that's important in dermatology, but it's not very important with germicidal UV because the UVC photons are heavily absorbed by the surface of the skin and the surface of the eye. So you don't have much backscatter. But this concept of fluence and fluence rate is important when we're talking about disinfecting microbes in the air, because you have a lot of photons coming in all directions, and the fluence can actually be a good bit higher than what you would read with an instrument. This is a sophistication, though, that normally is not important in practical safety. So what are the biological target molecules if we're talking about air disinfection or surface disinfection? Whether bacteria or viruses, there's a little difference because there are bacteria and viruses that have DNA, and then there are other viruses like the coronavirus in the past pandemic, which are just single-strand RNA. But in either case, it's one of the amino acids that it's been altered, and that will affect whether the biological molecule is viable or can divide or produce an effect. Another very important concept in photobiology is known as the action spectrum, which expresses the importance of wavelength. So in both photochemistry and photobiology, the action spectrum is describing the relative effectiveness of different wavelengths to produce the response, such as inactivation of a virus or death of a bacterium cell. And generally, the action spectrum covers a very limited number of wavelengths where a key biological molecule is absorbing. And normally this has a bandwidth less than 100 nanometers. There's normally a pretty strong cutoff at longer wavelengths because once you get to insufficient photon energy, there's no longer a biological effect. So the germicidal actions can differ, but generally act on DNA or RNA so that the DNA spectra is normally of note. There are some scientists that are convinced that in the case of the SARS-CoV-2 virus, there's a little shell of protein or lipid around the virus, and damage of that shell can inactivate the protein or the virus. So here is what has been referred to as the classical ultraviolet germicidal effectiveness curve. And this has been in many textbooks since the 1940s, when it was created by a scientist by the name of Gates. And it's based upon inactivation of a very common bacterium, E. coli. And you see it peaks somewhere around 265 or 270 nanometers. It's gone down to less than 1% by the time we get to the edge of the UVB action spectrum, around 315. And the red line here is the primary emission of the lamp that has traditionally been used for germicidal treatments. And that is the low pressure mercury lamp. And about 90% of the total radiant power output of this low pressure lamp is 254 nanometers. And so that particular lamp has traditionally been called the germicidal lamp. Now, with the advent of new optical technologies, new lamp technologies, we have ultraviolet LEDs under development, although they're still pretty much just in the research laboratory. And we have some other lamps such as the excimer krypton chloride lamp, which emits down around 222 nanometers, which is off this curve, because this only goes down to 235, which was one of the lines of the mercury low pressure emission spectrum. So there's, in actuality, slightly different action spectra when we talk about any individual microbe of interest. And this is a list of common natural molecules that I obtained from one of the specialist physicians who works with germicidal UV for many, many years. But also with the development of CRISPR technology, there's a lot more interest in what's referred to as bioterrorism, or some of these are traditional microbes that we've had effective treatments against, but also there's designer viruses that could be developed. And so there's more interest also in developing new and improved and safer germicidal UV technologies that could be used in the event of a bioterrorism attack.